After completing this chapter, the learner will be familiar with the configuration of a typical ship's fuel storage arrangement, be familiar with the configuration of a typical ship's fuel transfer system, know the problems associated with storage of fuel on board ship. As we will see later in the module, the actual fuel storage and transfer system for any individual ship will be dictated by the type of machinery fitted, the trading pattern, and the trading area, amongst other things. In this section we will look at some typical common arrangements for handling fuel on board ship, but you should always make yourself familiar with the actual systems on board your ship if you are involved in bunkering or fuel transfer operations. Recent amendments to MARPOL Annex 1, which came into force in August 2007, have introduced a requirement for all ships with a total fuel capacity of more than 600 cubic meters delivered after the 1st of August 2010 to have fuel tanks located inside of the double hull structure. This effectively means all ships ordered from the date the amendment came into force. The amendment also limits the maximum capacity of a single tank to 2,500 cubic meters. The purpose of this is to limit the pollution potential of these ships in the event of a grounding or collision incident. Traditionally, fuel storage tanks have been referred to by names related to the position of the tank within the ship's structure. The list gives some common examples. The introduction of the recent MARPOL amendments regarding double hull requirements for new vessels mean that the fuel tanks will have to be contained inside the inner hull for new vessels. The traditional names no longer describe the tanks accurately. Double bottom and wing tanks will no longer exist as such. Many vessels have already adopted a simple system numbering the fuel tanks from forward and identifying them by port and starboard location. Move the pointer over the illustrations to see the various fuel tank names for a single hull vessel. There are many different arrangements for onboard fuel storage, and the example used in this module is a typical general arrangement. Remember, you should always familiarize yourself with the actual arrangement on board the vessel you are sailing on. When planning the fuel storage arrangements, the ship designer needs to consider a number of factors. We have already stated the main factors, which are the type of machinery fitted and the fuel types required, the trading pattern, and the trading area. Consideration must also be given to segregation of different fuel grades and to the effect on the ship's list, trim, and stability of using fuel during a voyage. You will appreciate that it would be no use having a single tank for all of the fuel, or having all of the fuel tanks arranged down one side of the ship. The storage tank positions are also selected to minimize the risk of pollution in the event of collision and to minimize fire risk. The recent MARPOL amendment mentioned earlier is an example of this, with the need for double hull arrangements on new ships. It is not permitted to use either the fore-peak or after-peak tanks for fuel storage. Move the pointer over the illustrations to see the various fuel tank names for a double hull vessel. A fuel tank requires certain fittings in order that the fuel system is safe and meets the vessel's requirements for storage and transfer of the fuel. The items given in the list should be considered as the minimum requirement for fuel tank fittings. Other fittings which you may find fitted to the fuel tanks on the vessels you sail on may include remote reading content gauges, heating coils, and temperature and level alarms. The exact specification will depend on which classification society the vessel is classed by, as well as any flag state requirements. You can learn more about some of these fittings by clicking on the buttons. All fuel tanks must have an air vent arrangement to avoid the risk of overpressure or partial vacuum occurring in the tank. The arrangement should allow the air to exit when filling the tank and enter when taking fuel from the tank. The vent pipe should have a diameter 25% greater than the filling line. The vents should be positioned in an area where there is minimum risk of ignition of any vapors exiting the vent. As a further safeguard, a flame screen, normally a wire mesh, should be fitted to the outlet of the vent. Since the vents are normally positioned on an open weather deck, there is a risk of water entering the tank through the vent during rough weather. To prevent this happening, the vent head will have a valve fitted, usually either a ball or a disc-type float valve. During normal conditions, the float will remain in its lower position. If the deck area in the vicinity of the vent becomes flooded, the float will rise onto the seat, closing off the vent pipe. You should be familiar with the vent arrangements for your vessel and the maintenance requirements for correct operation. Click on the buttons to see the operation of the vent. When the fuel is delivered on board, it will contain impurities, such as dirt and water. In time, these will settle out in the bottom of the tank, forming a residue of sludge. It is necessary to manually clean the tanks regularly to remove the sludge, to prevent too much accumulating. In order to do this, the tank must be provided with a manhole door to allow access. If you are involved in cleaning fuel tanks, you must observe all of the requirements for entering and working in an enclosed space. These requirements are shown in the list. Make sure you are familiar with the requirements for tank entry on each vessel you sail on. In the event of a fire, the fuel tank suction valves need to be closed to prevent the contents of the tank feeding the fire. Whenever the fuel tank suction valves are in the same space as the machinery that they are supplying, it is necessary to have remote-operated, quick-closing valves fitted. This ensures that the valves can be closed even if the fire is in that machinery space. The quick-closing mechanism must be of an approved type. They can be operated by various means. Pull wires, hydraulic and pneumatic actuators, or solenoid valves are commonly used. Controls for all of the remote closing valves, as well as ventilation fan and pump emergency stops, are usually placed in a common emergency station. The valves and stops should be tested regularly to ensure correct function, and you should make sure that you are aware of the operating procedures on your vessel. Click on the button now to see the valve tripping action. Most ships' fuel tanks are fitted with sounding pipes, although classification societies do allow alternate arrangements, as long as they are of an approved type. Sight glasses and direct reading contents gauges may be used instead of sounding pipe arrangements, but they must have automatic closing devices to avoid spillage in the event of failure. This is usually achieved by fitting spring-loaded, self-closing cocks at the tank connection. Where sounding arrangements are used, the Classification Society rules give preferred positions for the sounding pipes. For sounding pipes which are positioned in the engine room, the rules require that they are fitted with self-closing cocks, usually of the gravity close type. The sounding pipe must also be fitted with a test cock positioned below the self-closing cock, so that you can check for high level before opening the self-closing cock. There are other fittings commonly found on fuel tanks, and these may include: fuel storage tanks should be fitted with high-level alarms to prevent overfilling unless an overflow arrangement is provided. Low-level alarms are also sometimes fitted to avoid running transfer pumps dry. Settling tanks and service tanks are always fitted with low-level alarms on vessels classed for UMS operation. A heating facility has to be provided for all tanks used for heavy fuel oil, usually in the form of steam or thermal oil heating coils. High-temperature alarms may be fitted to fuel tanks to warn against high temperature of the fuel. Where the heating medium temperature can exceed 220 degrees Celsius, a high-temperature alarm must be fitted. A temperature indicator should be fitted to all tanks that can be heated. Remote indicators for fuel tank contents are common on most vessels. However, when bunkering they should be used with care, and sounding should be taken to verify the readings, especially when topping off tanks. A drain facility is necessary for settling tanks and service tanks to allow water and sludge to be removed. A suitable save-all should be provided to catch any spillage. A save-all should also be in place around fuel filters and pumps to contain any oil during maintenance. There is no point filling the fuel storage tanks if the fuel cannot be transferred to where it is to be used. A suitable transfer system, which will allow transfer of fuel from any location to the settling tanks, is required. The system should have at least 2 transfer pumps, each of which is capable of transferring fuel at a greater rate than the maximum consumption rate of the machinery installation. Suction strainers are required at each pump. Suitable valve and piping arrangements will be included to allow transfer to and from, and isolation of, all the tanks in the system. There will normally be provision for separate transfer of each grade of fuel. It is usually possible to cross over systems by removing blanking plates in the event of pump failure. A typical system is shown here. You can compare it with the system on your vessel. You will notice that it shows diesel oil double-bottom tanks. These would not be allowed in future new builds. The tank arrangement for fuel storage should allow the different grades and new batches of similar grades to be stored separately. It should also have the flexibility to maintain vessel stability as fuel is used during a voyage. Depending on operational requirements, most seagoing vessels now use at least 3 grades of fuel. The majority of main engines operate on heavy fuel, but will need to change over to distillate fuel prior to maintenance or when the heating facility is unavailable. Many auxiliary engines now use the same grade of heavy fuel as the main engine. Others use a lighter grade of heavy fuel or a distillate such as diesel or gas oil. Also, there is an increasing need, due to legislation such as MARPOL, for operation on low sulfur fuels in certain trading areas. We will say more about these low sulfur fuels in a later chapter. You need to be aware of the grades used on board your vessel so that you understand the storage and handling requirements for the fuel. The problems associated with storing fuel on board a ship have increased with the wider use of residual fuels from more aggressive refining processes. Generally, the fuel quality has deteriorated, and with this deterioration, there have been a wide range of issues to deal with. You can learn more about the most common problems by clicking on the buttons below. Microbial contamination of diesel fuel oil has unfortunately become a common occurrence. Microbes are microscopic living organisms and include bacteria, fungi, and yeast, all of which can cause problems in the fuel system. Bacteria, normally the main source of problems, can be either aerobic types which need oxygen to survive, or anaerobic types which do not need oxygen. When bacteria are present in water-contaminated diesel fuel, colonies can form as slimy masses at the interface between the settled water and the fuel. As the colonies break up, they can be carried through the fuel system, causing severe filter blockages. Aerobic bacteria usually initiate the problem, but as the oxygen supply reduces, anaerobic bacteria can appear with the colonies growing rapidly. These anaerobic bacteria produce hydrogen sulfide, which is toxic and highly corrosive. We will look at ways to deal with the problem in a later chapter. In many cases, the fuel delivered to the vessel will consist of a number of different components from the refinery process, which have been mixed together in order to meet the specification given in the fuel standard. Heavy fuel oil, with either viscosity or density values outside of the limits of the fuel standard, may have distillate fuel mixed with it to try and improve its condition. If the mixture is not stable, then the two components will separate out during storage, leaving the heavy fuel component in the lower part of the tank and the distillate above it. Obviously, the high values of density and viscosity may cause problems when transferring or pre-treating the fuel before final use. You can reduce the risk of this occurring by ensuring that the fuel storage temperature is not excessive, as this may accelerate any separation. If you have studied CBT number 179, Marine Fuel Properties 2, then you will remember that fuel oil can be contaminated from a number of sources. These include the raw crude oil, the refining process, and the transportation and storage stages of supply. Some of the contaminants are solid material, including sand, soil, rust, and other debris. Water, either salt or fresh, is also often present in the fuel. During storage, some of the water and dirt will settle out and collect in the bottom of the tank. This has to be removed, either by draining or manual cleaning, so that it doesn't carry over into the fuel systems. It also means that there has to be suitable filters and pre-treatment facilities on board to remove any remaining water and dirt which has not settled. You will learn more about these facilities in a later chapter of this module. Incompatibility is the term used to describe a situation when two different batches of fuel, each of which is normally stable, react when mixed together, resulting in heavy sludge deposits in either the storage tanks or in the pre-treatment equipment. The result of this condition can be that the fuel becomes unusable and the vessel's operation is seriously affected. Severe sludge accumulation in the fuel treatment equipment, resulting in more frequent cleaning, can mean that the treatment rate cannot keep up with consumption requirements. It should be standard practice when bunkering a new batch of fuel that it is only loaded into empty or nearly empty tanks. Mixing with previous bunkers should be avoided whenever possible. In this chapter, we have seen the kind of facilities required for receiving and onboard storage of fuel oil. We have looked at the tank arrangements, including the fittings required, which make the arrangement suitable for storing fuel safely. We have considered possible transfer systems for moving the fuel from tank to tank. We have also looked at some of the common problems associated with onboard storage of fuel. In the next chapter, we will be looking in detail at the bunkering requirements and procedures that are in place to help make onboard fuel handling operations safe and pollution-free. Before you move on, you should complete the end of chapter assessment. This will give you an indication of how much you have learned so far.